Hey, good afternoon, everyone. Um, oh, I heard someone didn't mute yourself. If you didn't mute yourself, please mute it. So today, I I didn't play the music, but I provided a link here, so you can watch it by yourself or listen it by yourself. It's Torsion. So today I featured this music that is Torsion. It's actually the trailer music of Avengers, the end game. Okay. I hope you can feel the torsion in that music. But today we will talk about torsion is in mechanics of materials. Okay, we will analyze the stress and deformation in torsional elements. But our objectives today will be two, right? So we will analyze the torque and the stress in a torsional element. We will analyze the deformation of the torsional elements too. Okay, so this is a new chapter. So in previously in chapter 3, we talked about axially loaded elements. And there we have learned how to calculate, we had 3 steps, right? It's using free body diagram to find the internal forces. Right? Then we determine the cross-sectional area so that we can calculate the stress. Right, but here in this chapter 4, we will study torsional elements. It will be a different story. Okay, here the internal force will not be the axial forces anymore. So it's torque, right? So the torque, when you apply a torque to a shaft, we normally call the element that is subjected to torsion shaft. Okay, so when we apply the torque, then a shear stress will be generated, only shear. So it's the let's look at this thing. If we consider this a bar, so I will apply torque to twist it instead of pushing to shorten it or stretch to elongate it. Okay, this will be different story. Okay, in this chapter, since we're only applying torque, not compression or tension, so this thing will not become shorter or longer, right? It will only be twisted. So the generated stress will only be shear stress, and the strain will be angle, right? So the deformation will also be an angle. So the twisting is reflected by at a specific cross section, reflected by a twist, angle of a twist. Okay, those are the features, the characteristics of torsional elements. So the stress, the force will be torque. So stress will be shear stress, and the deformation will be an angle of twist. Okay, so this will be totally different from axially loaded elements. So this will be our chapter 4, torsion. And in this first section, we will just try to define the stresses and calculate the stresses in torsional elements. Okay, I provided you a short video, the link to a short video. I hope you have watched it, in which you can see a lot of examples of torsional elements. So basically, torsional elements are frequently used in machines and vehicles, especially in power transmission systems. Right? So it's actually a shaft, right? Normally we just deal with a shaft. You can see that sometimes the shaft is cross-section is a circle, right? So its cross-section can be a circle, so we call it a circular shaft, and sometimes tubular shafts, right? And sometimes its cross-section can be other shapes or any random shapes, right? But these random shapes or square rectangle shapes will not be considered in this chapter, in this course, okay? We will not consider these other shapes in this course. We will only consider these solid circular shaped shafts and tubular shafts, okay? We will only consider these two situations, two scenarios. Okay, so in these kind of elements, and they will be subjected to torques, then you will generate the shear stresses and angle of twist, as I mentioned, right? So let's just look at this, the first simple example as shown here. It's a simple shaft, one end fixed at point A, and we're adding a torque to the other end B, and the overall length AB equals L. Okay, so at the point A, the end A, we fix this shaft, meaning that at this point, no deformation is allowed. Right? So this plane at point A will be fixed there. No any deformation is allowed to it. Okay, so let's compare it with a axially loaded element. Okay, so in chapter 3, we talked about axially loaded element. That is just, let's consider a similar thing. A element is shown here, and we add a load to this end. Let's call it F. Okay, so when we load it, let me ask you the first question. In this axially loaded element, when we add this load to one end of this element, is the internal force the same along the length of this element? In other words, if I cut it from this location, location 1, location 2, are the internal forces the same? So I saw Jackson Riggs. Hey, Jackson Riggs.
Yeah.
Yeah, so this is my question. So let's look at here, this axially loaded element. If we cut it from position 1 to position 2, do you think the internal forces are the same as these two locations?
I don't think they are. If it was a free beam, it would be, but since it's cantilever, I think the internal forces are different across those two sections.
Internal forces? Why just okay, we determine internal forces using free body diagram, right?
Right.
So if we're looking at position 2, we cut it at position 2, make it free, and you add the internal force here, let's call it F2. Right, the free body diagram, after that, we will have an equilibrium equation. Right? What is the equilibrium equation? That will be negative F2 minus F equals 0, right?
Right.
And if, how about position 1? If we cut it from position 1 to make it free, we add the internal force here outward, F1. So this one is gone, okay? So the equilibrium equation will be negative F1 minus F equals 0, okay?
Okay.
So are F1, F2 the same?
Yeah.
Yes, okay. So let me ask you the second question. Look at this torsional element, this shaft shown here. When this left end A is fixed and you add a torque to the point B, and if we cut it from here, location 1, location 2, do you think the internal forces or internal torques in this case, do you think they are the same?
Yes.
Yes, okay, good. Okay, so that is my question, my first set of questions. Okay, then look at the second set of questions. Is the stress uniform on the cross section, on this cross section? Okay, let's look at the axially loaded element first. If we consider this element is cross section is a square. So are these internal or are this stress, the normal stress uniformly distributed through this area? Right? Strictly speaking, if you learn elasticity and plasticity, strictly speaking, it could be non-uniform. But in mechanics materials, we assumed that the stress is uniformly distributed through this cross-section area, right? So in the case of normal stress, axially loaded elements. But here, in the torsional elements, look at the cross-section. It's a circle, right? It's a circle, it's shown here. So is the stress uniformly distributed on the cross section? So do you think this shear stress, as I mentioned, the shear stress is uniformly distributed on this cross section? Okay, for our first question, the answer is yes, right? But for the second question, the answer this time would be no, right? So this time in the first equation, the answer is the same as that way in actually loaded element. But for the second question, it would be different, okay? We will show that why it's different, because at the centroid, right, this shear stress will be 0, and on the edge, it reaches its maximum value of the shear stress, okay? So between these 2 points, it's a linear distribution, okay? So this shear stress is linearly proportional to the distance from the centroid of this cross-section. Okay. Then the third question regarding this would be how to apply a torque, right, to a shaft. Right? So if we have a bar actually loaded element, if you want to load it, you can just simply stretch it or push it, right, to apply tension or compression. But for a shaft, right, so how to apply torque to it, and we have some other different types of methods. As shown here, you can use arms and then add loads to it. So you will generate these moments, right? This moment when you add them together. But in this case, you have two, right? 2 arms and 2 forces. Then you will need to add 2 moments together. That is the torque applied to this shaft, right? So in other cases, in later sections, you will see that we can also use pulley or gears to apply the torques to a shaft. Okay, so this slide showed you the basic assumptions in the theory parts, in the theoretical parts of torsional elements. In previous semesters, I tried to derive the core equations for torsional elements, but I found that perhaps 90% of students are not interested in this theoretical parts. So I will skip the derivation of the equations and just show you the equations, and let's explain using many examples, like how to use the equations to calculate, to solve some problems, okay? So I've provided the steps for the derivation of the equations for the stress calculation and later for the deformation, the angle of twist calculation, okay? For that 10% of students who are interested in the theory, okay? You can just go through these steps by yourself, and if you have trouble understanding the steps, just let me know so we can schedule a Zoom meeting to talk about it. Okay, so basically in a torsional element, we assume that at one end is fixed. Right, this derivation starts from this point, right? You assume this end is fixed, then you apply a torque to the other end, then this thing will be twisted, right? So you can see that the angle of twist is called phi, and it's a function of x. So x equals 0 at the fixed end, and it increases following the direction of x, right? So this phi x, this angle of a twist, also increases linearly following the increasing of x. Right? So this is a basic assumption. So based on these assumptions, we can derive the equations as shown here. Okay. To summarize it, we will have 2 equations to use to calculate the shear stress in the torsional element. Okay. So I highlight that again. In this chapter, in torsional elements, we're not adding any axial loading to this shaft. Okay, it's not a bar. Also, it looks the same as the bar as the actually loaded element in chapter 3, but we're not adding any axial loading to it. Okay, it's only subjected to torque. So the stress generated will only be shear stress. So no normal stress generated in this bar along the longitudinal direction. Okay, those 2 equations are shown here. The first equation is used to calculate the maximum shear stress. That is tau max equals Tc over J. Okay. The second equation is to calculate the shear stress at a random point where this point its distance from the centroid of the cross-section is rho. Okay. So in these 2 equations, this T is the internal torque in the shaft, and the C is the maximum distance from the from the centroid, and the rho is just the distance from the centroid. Okay, it's the distance of the point at which we're calculating the stress from the centroid of the section. Okay, the C is the maximum value of rho. Okay, so here C equals the maximum value of rho. Okay, so this has been clearly illustrated in the figure here. So you can see that according to this equation, at the centroid or the center of the circular shaped shaft of the cross section of a circular or tubular shaped shaft, at the center, obviously rho equals 0, right? So tau equals 0. Right? When this rho increases to some random point as shown here, so the tau equals T times rho over J. And when it reaches the edge, so here the rho equals C equals half of the diameter or the radius of it, right? So here the tau reaches its maximum value equals TC over J. Okay, these are these different situations, 3 scenarios. Okay, then here the internal torque T is determined using free body diagram. Okay, you should have learned that in statics. So later we will review the whole process. Okay, then the other parameter here we will need to use is the J, which is called polar moment of inertia. This is the J, polar moment of inertia. Okay, in these steps, you can see here, if you review these steps, so we derive the equations, you can see that we have derived this J. Okay, so how did we derive this J? It's just here. It's from integration. It's a surface integral problem. Okay, we can derive it, but if you do not want to derive it, you're not interested in the theory, you just have to remember these 2 equations. Okay, no other ways. You have to remember these equations. This J, polar moment of inertia, its nature is kind of geometric or sectional property of this cross section. Okay, it's a geometric property of the cross section. Okay, so if it's a solid shaft, this J equals pi over 32 times D. This is the diameter to the force. Okay, for a tubular shaft, this J equals pi over 32 times D. This is the outer diameter, and this D is the inner diameter. Okay, so if it's a tubular shaft, this J equals pi over 32 times this outer diameter to the force minus inner diameter to the force. Okay, these are just 2 equations to calculate the sectional property. Okay, when you have determined the internal torque using free body diagram, when you have determined this sectional property, this J or polar moment of inertia, when you determine the position, when you know the location where you are determining the stress, you can determine the rho or the C. Then you can use the equations to calculate the stress. Okay, to summarize that for the stress analysis in torsional elements, so we have 3 steps. The first step is to determine the internal torque using free body diagram. Second step is to determine the polar moment of inertia, that is the geometric property or sectional property, right? Then the third step is determine the shear stress caused by the torque. Okay, these steps are actually very similar to the 3-step algorithm we used in chapter 3 to do the stress analysis in axially loaded element, right? In chapter 3, in axially loaded element, our 3 steps, okay, let's review that. The first step, free body diagram to determine internal force F, right? The second step to determine A. right? Here the first step can be V, can be F, can be V, right? And the third step will be just normal stress equals F over A, or shear stress equals V over A, right? These are these three steps, right? Three steps, not actually loaded element. If we're talking about the shear, right? It's just a general stress analysis. General stress analysis problems. Okay, we follow these three steps. You can compare this with this stress analysis algorithm in torsional problems. Here you can see the first step, still free body diagram to determine the internal force, but this time this internal force is a torque, right? It's not F or V. And in the second step, we still determine the sectional properties, but this time it's not an A, it's a J, the polar moment of inertia, right? Then the third step will be the same, use a specific equation to calculate the shear stress. This is only shear stress. Okay, the equation is listed here again, but strictly speaking, this is the general equation is tau equals T rho over J. And in this equation here, the C is just the maximum rho, okay? Here we should use rho. This is the distance of the point at which the stress should be calculated from the centroid of the section. Okay, in the three steps, the first step is free body diagram. As I promised, let's review the process to use free body diagrams to determine the internal torques in this torsional elements. Okay, I provided a example here. So you have three sections. Then it's A, B, C, D. Right? It's point A is fixed. Then at point C, B, and D, you add three external torques. Okay. So here we will follow the three steps. Again, this is very similar, if not the same as the previous steps. Okay, the step one, cut the element to make it free. Okay, cut the element to make it free. You should pick the point where you're determining the internal torque, right? So cut it there to make it free, then add the add the internal torque outward. Again, just add it outward, okay? Then apply forces, then use equilibrium equations to solve the internal torque, okay? So let's look at this example, okay? So we're determining the internal torques between AB, between BC, and between CD. Let's look at the internal torque between AB first. Let's call it T1, okay? So to do it, the first step is to cut it between A and B, right? Then cut it to make it free, and we will get two parts, right? The left part is associated with this fixed end, right? So to use that, you have to solve the reactant forces, right? The restraints, solve the reactant forces. So you will need one more step, right? So the better choice is to use the free part, the right-hand part, the right part, okay? Cut it, make it free, then we can add the internal torque outward. Okay, so here we normally use double-headed arrow to denote a torque, right? So in the figures, you can also use the arrows as shown here. This is also the other way to denote the torque. We have two ways to denote a torque in a figure, right? It's either this TB manner or a double-headed arrow. Okay, these two methods are connected using the right-hand rule. Okay, let's review this right-hand rule. As look at the figure here. We use our right hand. Right, it's to curl your four fingers according to the direction of the torque, like a TB, TC, and TD. Then the direction of your thumb will be the direction of the double-headed arrow. Okay, so in this way, the internal torque we added, this double-headed arrow, is equivalent to a T1 that is in the opposite direction to that of the TB, right? So if you use the other method to denote it, it will be something like this. Okay. So just knowing this, be familiar with the right-hand rule. Then let's look at the first section, the first section AB. Right? Just when we cut it to make it free, we got it here. Cut it to make it free, and we have added this double-headed arrow T1. Then what is the direction of TB? What is the direction of TB? Left or right? So you can comment there using our chat function. Okay, here there's a TB. Look at the TB here. Let's we use our right hand, curl your four fingers according to the direction of the TB, then your thumb will be pointing right, right? Okay, I saw some students are saying that it's right, right? It's right. Okay, so how about TC? TC is also pointing right, right? TD is also pointing right. So based on the first figure, so we will, the first free body diagram, we will be able to get a equilibrium equation that will be negative T1 plus TB plus TC plus TD equals 0, right? So the T1 equals TB plus TC plus TD, right? So in the similar way, you can do the T2 and T3. Okay, so obviously here, the T2 equals TC plus TD. And here, the third free body diagram, you can derive that the T3 equals what? Equals TD, right? So this is how we do the free body diagram and determine the internal forces, internal torques. Okay, those are all theories. And then later, let's go through some examples. So the first examples will be, first three examples will be very simple. Okay, let's go through them very quickly. The first one, okay, while removing a wheel to change a tire, so a driver apply forces P equals 100 Newton at the end of two of the arms of a lug wrench. So as shown in this figure. So assume each arm of the wrench is A equals 225 millimeter and has a solid circular cross section of diameter D equals 12. Determine the maximum shear stress in the arm that is turning the lug nut. Okay, this is a very straightforward calculation. Okay, we're requested to determine the maximum shear stress. Okay, maximum shear stress is just a tau max. Right? And we had this equation already. So the tau max equals what? T times C over J. Right? So the key is to find what is the T, what is the torque, right? So here you don't even need to use a free body diagram since you have provided all of this information so you can calculate the torque, right? Here the torque equals, and the figure is here, we're applying 2Ps, okay? We're applying 2Ps to it, and the arms on both sides are the same, that is A, right? So the T equals what? Equals P times A times 2, right? We have two of them, right? The P is 100 Newton times A is 225 millimeter times 2. All right, so we will have 45,000 Newton millimeter. Okay, then the second parameter, that is the C, Right here, the cross section is a circle, and the C, the maximum value, maximum possible distance from the centroid of this circular cross section. So that is the radius, or half of the diameter, right? This is D over 2. That is 6 millimeter. And the J here, okay, we have that equation already, right? This is pi over 32 D to the 4th. Right? So that is pi times 12 to the 4th over 32. Okay, this is 2035 millimeter to the 4th. Okay, then in the end, we can just use this equation to calculate the maximum shear stress. That is TC over J. That is 55,000 Newton millimeter times 6 millimeter over 2035 millimeter to the 4th. And the result, if you use these numbers, the result will be 132.7. Okay, here's my question. What is the unit? What is the unit of this result? Jacob Hensler.
Newtons per millimeter squared.
Okay, this is newtons per millimeter square. What is known as the other name of it? What is that? Wait,
I don't know.
I said we normally use, we like to keep the units used in calculations consistent, and we define a consistent unit system. Right? In that system, we have Newton, millimeter square, and what? MPa, right? Newton per millimeter square, that is megapascal, MPa. These are equivalent to each other. Okay. Yeah, but Newton per square millimeter, that is also correct. This is no problem at all. I just need to know, be familiar with this unit systems. Just Newton per square millimeter equals MPa. Okay, this is the first example, and the second example, very similar to it. Let's look at it. Okay, the pipe AB shown in this figure has an internal diameter of D equals 80 and outer diameter D equals 100. So if its end is tightened against the support at A using a torque wrench at B, then determine the shear stress developed in the material at the inner and outer walls along the central portion of this pipe. And the PDDBA has been given. We asked you to calculate two things. That is the shear stress, or maximum. Let's call it maximum. Material the inter outer wall, so not maximum. It's just that they have pointed out these locations, right? So we're determining this shear stresses as the internal wall here, outer wall here. Okay, so these rho values or C values have been provided, right? So rho values or C have been known. So here again, so we're calculating the shear stress or maximum shear stress, since they are requesting you to calculate these two values. One is the inner diameter, the other inner radius, the other is the outer radius, right? So we can use these equations. The tau equals T rho over J, right? Then this T here, let's calculate the T first, right? The T here, this is very similar to the first example. We have two arms, two P's, but this time these two arms are not the same. Okay, one is A, the other is B. Right? So T equals PA plus PB. Right? That is 80 Newton. 80 times A, that is 300 plus 80 times 20. Okay, here you get 40,000, right? 40,000 Newton millimeter. Then the J is a constant value, that is pi over 32. This is the tubular shaft. It's the outer diameter to the force minus inner diameter to the force. Right, this is 100, and this inner diameter is 80. Right. So our result will be 5.796 million millimeter to the force. So the stress at the outer wall where the rho equals what? The outer wall, the rho just equals the outer diameter over 2, right? D over 2, that is 50 millimeter. So here the tau equals just 40 out, right? 40,000 times 50 over 5.796 million. Okay, here you will get 0.345 MPa or Newton per square millimeter. Okay, this I directly use MPa. Since here just in these calculations, the units will be Newton and millimeter. And the stress at the inner wall, where the rho equals inner diameter over 2, that is 40 millimeter, right? So this tau inner will be 40,000 Newton millimeter times 40 over the same J, that is 5.796 million. Right, so here will be 0.276 MPa. Okay, so the example 1 and example 2 are very similar. They're just straight calculations, but you just need to figure out which equation to use, okay? Especially which equation to use to determine the J, the polar moment of inertia. And example 3 is a simple design problem. A solid circular shaft is subjected to a torque 9,200 pound-inch. So the maximum allowable torsional shear stress generated is 13,000 psi. You'll find the required diameter for the shaft. Okay, so this is a design problem or an inverse problem. Okay, is the equation that is used to solve this will still be the same, right? This is tau max equals T times C over J. We're determining allowable diameter, that is D, right? D is just what? This is the C 2 times C, right? So we're just actually determining this D. So this is the equation, and we have known that the allowable torsional shear stress is 13,000 psi. So this has to be let's make it so it has to be no higher than this 13,000 psi. Okay, here this is C equals D over 2. And J is pi over 32 D to the fourth. Right, so this tau max can be rewritten as T times D over 2 over pi over 32 D to the fourth. Okay, so this will become 16T over pi D cubed. Right, so from here we can derive that this D cubed equals 16T over tau max times pi. Okay, so this will be 16 times the torque has been given 9,200 pound-inch over the tau max has been given. Tau max is 13,000 psi pounds per square inch, right, times pi. Okay, so this will be 3.6 cubic inch. So D can be solved as 1.52 inch. Okay. So this is the number, the value of D. Okay, the value of D determined from these equations. But our final report should be what? Should be a limit, right? So to be safe, to make sure that this element, this shaft can safely carry this allocated torque, 9,200. So you have to make sure that the D diameter should be not smaller than 1.52 inch. Okay, so larger the safer, right? To make it safe, this is the lower limit of the size of the diameter of this shaft. You have to make sure that this diameter, we'll do a design, okay, make sure that the diameter is larger or no smaller than this calculated limit size. And example 4 will be, so we will need to use all of these steps to do the stress analysis, okay, in this torsional element. Okay, here the example 4, a D equals 20 millimeter diameter solid steel shaft is subjected to the torques shown in this figure. Okay, this is very similar to what we used to illustrate the process, right? This is the previous example. It determines the maximum shear stress in this shaft. Okay, so determine the maximum shear stress in this shaft. Okay, so we have known that the tau max equals TC over J, right? This is what we have known, the central equation. But here in this, through this whole shaft, we have only one shaft, right? We have only one shaft, meaning that the C will be a constant and the J will be a constant. So where can we find the maximum shear stress? Is that where we have the T max, right? Where we have the maximum torque, there we have the maximum shear stress. So we're actually determining the maximum torque. Okay, so where is the maximum torque? To find the maximum torque, we have to know what are the values of the internal torques. Right? We have how many sections here? We have section 1, section 2, 3, and 4. We have 4 sections. Right? So you have to do 4 free body diagrams and to determine the values of these 4 torques, and then select the maximum one to do the calculation. Right, so this is the analysis. Then let's see how to get the maximum value. Right, so as I mentioned, the first step always be by free body diagram. Free body diagram. Okay, so the first one, let's look at section 4. Okay, let's look at section 4. If we're determining the internal torque in section 4, we have to cut it here and make it free, right? And add this internal torque outward, right? So this will become something like this, right? So we're adding a internal torque outward. This is the T4, and at the point E, we have a external torque, right-hand rule. Curl your 4 fingers according to the direction of this torque, TE, then your thumb will pointing left, right? So you will have TE pointing left. So here in section 4, we can write a equilibrium equation that is negative T4 minus TE equals 0, right? So T4 equals negative TE. That is negative 14 Newton meter. Right, this negative, just to be clear, what does this negative mean? Right, what it means. This negative means that the true internal torque will be along the other direction. Will be along the other direction. It's opposite to what you set in the beginning. Right. Okay, here's the second step. Let's look at section 3. Okay, in section 3, we cut it from here to make it free, and add the internal torque outward, right? So we will get such a section, and you have point D and point E. Right, so we add this internal torque T3, and then what is the TD? Right, the TD, use your right hand rule, TD will be pointing right, right? This is our TD. The TE, the same as above, the pointing left. So here our free body diagram will result in a equilibrium equation that will be negative T3 plus TD minus TE equals 0. Right? From here, T3 equals TD minus TE. Right? TD is 24 minus 14. Right? That will be 24 minus 14. That will be 10 Newton meter. Okay, then the next step, section 2. When we cut it from section 2, okay, we can get a very similar thing as shown here, but it will have point C, point D, and point E. Right, so the internal torque T2, and at the point C, right hand rule, right, right hand rule, the C will be, TC will be pointing left, TD pointing right, TE pointing left. Right, so here, based on this analysis, we can get negative T2 minus TC plus TD minus TE equals 0. Okay, so T4 equals T2 equals negative TC plus TD minus TE. Right, and the TC is 35 right here, so the result will be negative 25 Newton meter. And the last step, section 1. Right, section 1, just cut it here, make it free. So again, just let's repeat this process. So you will have point B, C, D, and E. right? Here you will have many torques, right? It's the internal torque T1 and TB, it's a right-hand rule. TB will be pointing right, C pointing left, D pointing right, the E pointing left, right? So the long equation will be negative T1 plus TB minus TC plus TD minus TE equals 0. Okay, so here we can derive that T1 equals 24 Newton meter. Okay, so here we have derived this four internal torques. As I mentioned in the beginning, we just need to figure out which one is the biggest value, which one is the maximum torque. Okay, here we have four results already. Negative 14, 10, negative 25, 24. So which one is larger? Which one is the largest value of the internal torque? Does the negative sign, positive sign matter? The signs doesn't matter, right? Since we're just calculating the stress, maximum stress, the signs doesn't matter here. Since the signs only meaning that the direction only means direction. Is the direction the same as what you assumed in the beginning, right? So here, the maximum value would be here, right? So this is our winner. So negative 25 or just 25 Newton meter, okay? So second step, we just calculated the sectional properties. That is J equals pi over 32 times D to the fourth. That will be 15,708 millimeter to the fourth. And our C will be just a half D. It will be 10 millimeter. So the final step, maximum shear stress will be T max times C over J. Right? So our 25, okay, T max here. T max, as we determined, that is 25, what, 25 Newton meter, okay? Newton meter. As we mentioned, I just highlighted again, as we mentioned, here just we're using consistent unit systems, okay? Here we have Newton meter, okay? This is determined as Newton meter. So we will need to convert it into Newton millimeter. So this will be 25,000 Newton millimeter. Okay, so here in this equation, we will have 25,000 Newton millimeter times 10 millimeter over the J is 15,708 millimeter to the fourth. Okay, so our result will be 15.91. Okay, you can see that you have millimeter square above and you have millimeter to the fourth bottom. So you will have Newton per square millimeter again, or 15.91 MPa, okay, megapascal. Okay, so this is our example 4. It's actually another problem for straightforward calculation. Right? We just reviewed this we exercised the 3 steps: free body diagram, the determining sectional properties, and then determining the maximum stress. Okay, just normally we use just 3 steps to figure out the shear stress. Okay, so now this example 5 seems to be more complicated, but actually it's a okay level example. Okay, it's not that complicated. Since we'll not need to use integral, okay, we just only need to consider. Let's just check how to consider this distributed torque. Okay, in this figure, you have a aluminum solid shaft with diameter of d that is subjected to uniformly distributed torsional loading of T, and there's two concentrated external torque, TC and TD. So calculate the maximum shear stress at section E, located x equals 0.9 meter away on the right side of the restraint A. Okay, we're calculating the maximum shear stress here. Okay, so again, since maximum shear stress equals TC over J, right? This doesn't matter maximum T or not. Since this is a specific location, we just have a specific value of T, right? You just need to find the maximum possibility of rho, and that is C. Right? And J is also unique, is a constant. So here, to solve it, we just need to find what is the T, right? So what is the T? What is the T value at this location? And just free body diagrams. We just need a free body diagram to solve it. So here again, this is the first step. This is a free body diagram. Okay, we're calculating this, determining this location. We cut it from here, make it free. Then we get a left section and a right section. Again, just remember that which section we need to select. Of course, you can select both, right? Either one of them. You can select the left part or the right part. But if you select the left part, you have to solve this TA first, okay? You have to solve the TA first, determine the reactant forces, reactant torque at this restraint A. And then you can determine the internal torque. You need two steps, okay? So if we're selecting the right part, the free part, so we just need one step, okay? So we will just focus on the right part in this example. Cut it, make it free, and then you can just see that we added this internal torque T at here. Then we have converted TC and TD into double-headed arrow. Again, just using your right hand, and look at TD, curl the four fingers according to the direction, then your thumb will be pointing right. Right, so your TD will be a rightward double-headed arrow. And the TC, curl your fingers according to the direction, the thumb is pointing left. Right, so your TC has been simplified into a left pointing double-headed arrow. Okay, so then how about the distributed one, the distributed torque? Okay, the distributed torque, again, in the same way, you can use your right-hand rule. Okay, look at the direction here. You have five arrows is indicating the direction of this torque. Curl your right hand, curl your fingers according to the direction. So your thumb will be pointing right, right? So here will be the other one. Let's call it TBE. Right? This is a TBE, pointing right. Okay, so based on this free body diagram, we can get the equilibrium equation. Right, so that is negative T. Right, since it's pointing, the TBE is pointing right. It's just a plus TBE and minus TC plus TD equals 0. Okay, so what is this thing? What is the TBE? What is the value of TBE? So TBE is the distributed torque, and the T, the distribution is that, where the distribution T is here, okay? 6 kilonewton meter per meter, okay? So this is just a T times L1 minus X, right? So this is the value of the TBE. This is the distribution 6, the concentration, 6 kilonewton meter per meter times L1 minus X, that is the BE, right? So from here, we can derive that the T equals just T times L1 minus X minus TC plus TD. Okay, so here will be 6 times 2 minus 0.9 minus TC, that is 8.0 kilonewton meter, and plus 4. Okay. Okay, from here we can solve that. This is 2.6, but the unit will be the same as what had been used in the description, that is kilonewton meter. Kilonewton meter. If we convert it to Newton millimeter, that will be what? Kilonewton, 1,000, right? Meter to meter, another 1,000. So this will become 2.6 million Newton millimeter. Okay, so so we can just use our equation to determine the maximum shear force, shear stress, right? But before that, we need to know the C, right? The C is just pi over 2, that is 25 millimeter. And the J is what is pi over 32 times D to the 4th. That is pi over 32, 50 to the 4th. We get 613, 600 millimeter to the 4th. Okay, and the last step, just a tau max, and that will be 2.6 million times 25 over 613, 600. Okay, since these numbers, their units have been converted to Newton millimeter, square millimeter, etc., then we will have MPa directly, right? 105.9 MPa. So the last example for the stress analysis is a compound shaft, right? Consists of A equals L1. It's an aluminum tube joined to L2, that is a steel tube. Okay, so just both aluminum and the steel tube have an outside diameter of D equals 38, and the wall thickness of 3. And the shaft is secured by fixed support at the one end and is subjected to a torque of T at the other end. So the ultimate shear stress of steel and aluminum are tau US equals 145, and tau UA, that is the 180 MPa respectively. If the factor of safety required in this steel and aluminum are 1.67 and 2.5 respectively, determine the maximum torque that the compound shaft can carry. Okay, this reads very complicated. Let's simplify it. Okay, so they ask you to calculate the maximum torque that the shaft can carry. Okay, this we have the tau max. We're determining T max. Right? So how to determine T max? So from the original equation, tau max equals T max times C over J. Right? From this equation, we can derive that the tau max equals the allowable shear stress times J over C. Right? So this is the equation we will use to calculate the maximum allowable torque. And then what is allowable shear stress? That is the ultimate shear stress over factor of safety, right? So here, just everything had been clear. Since our tall steel allowable will be ultimate stress of steel over factor of safety. That is 145 over what, 1.67. That will be 86.8 MPa, right? Then the other one, just the aluminum allowable will be TUA over factor of safety. That is 180 over 2.5. That is 72 MPa. Okay, so we have determined two allowable shear stresses. So which one we'll use for this design, the larger one or smaller one? Okay, so you will not allowing any stress be higher than this minimum number, right? But it's a smaller number of this one. Right? Otherwise, this aluminum will be failing, will be fracturing, right? So we will need to select the smaller one for our design. So from this two, the allowable shear stress will be 72 MPa. Okay, then how to determine the T max, right? This, again, we will just need to use this equation, right? So where the J is just a pi over 32 d to the fourth minus d to the fourth, and that is the d is 38. Here d equals 38 millimeter, and the inner d just 38 minus 2 times 3, right? The thickness is here, minus 2 times the thickness, that will be 32 mm, right? So this J will be calculated as 101.8 thousand millimeter to the fourth. And the C is just 38 over 2, right, or 19 mm. So the tau max will be here, the tau allowable times J over C, right? The tau allowable is there 72 MPa, 72 MPa times 101.8 thousand millimeter to the fourth over C, that is 19. Okay, since we have been using the consistent unit systems, MPa, millimeter, etc., right? So directly we will get Newton millimeter, right? It's a 385,800 Newton millimeter. Okay, so if this is your design task, your final report should say that the T allowed by this system should be not higher than this T max. Okay. So those are just examples for shear stress analysis or design problems regarding this torsional elements. Then in the second section, we will talk about deformation. okay? So this is nothing unfamiliar, okay? This is very similar to the previous equations, okay? In the chapter 3, we have introduced 3 equations that you can use to calculate the deformation of axially loaded elements, right? So those are like a delta equals what? FL over EA, right? And you have the other one is just a sum of FI, LI over EI, AI, or integral 0 to L FX over EAX dx, right? Those are the 3 equations we used in chapter 3 to calculate the deformation of axially loaded element. So here is, if you are interested, I also share the process, the whole process to derive these equations for torsional element. But it's easier to remember it in this way, is to do analogy. I can do an analogy between these 2 sets of equations. You can see here in chapter 3, we used this equation, this delta equals FL over EA. Okay, the F is the internal force. L is the length, right? And E is the elastic property, right? The property, elastic property. And A is the area, but we can call it more generally, it's a sectional property. Sectional property. This is the material property. Okay, this is just 4 things. Look at this new equation. Look at our new equation. As we mentioned in the beginning, the deformation of a torsional element will be an angle of a twist. Right? Angle of a twist. That is the phi. Okay, we use phi to denote angle of a twist, which is the deformation in torsional element. Okay, you can see here we have also 4 terms. This is T, this is L, and G, and J, right? So what is the T here? The T is, again, this is the internal torque or internal force, right? This is torque in this case. Then the L, again, this is the length, right? And the G is the shear modulus or modulus of rigidity. Again, this is also the material property. And the J here is what is a sectional property. Right? You can see that these 4 terms actually belong to the same categories. Okay, just a T with respect to F, right? It's the internal force. L, and then G, modulus of rigidity with respect to E, modulus of elasticity. Those are material properties. And J here, sectional property, it is the polar moment of inertia. And in the axially loaded elements, those are the A, sectional properties or area of the cross section, right? So the rest, I think you can understand them logically, naturally, since the second equation will be just dealing with multiple section problems. When you have 2 or 3 sections, where we add a torque to this end, then you would just calculate the angle of a twist of each of them, then add them together, so you will get the overall value. And the third case will be an integral, so that when you have variations of any one of them, variations of the torque of the J, etc., then you can use integral to calculate the overall deformation. And here's in this steps, you have several steps about how to calculate the torsional deformation. The one thing is that you need to be familiar with the sign convention here. So what is a positive angle of twist? What is the negative angle of twist. So this is tied to the angle, the sign convention of the torque. Okay, so an internal torque is positive if a double arrow goes outward from the sectioned surface. Okay, this is just the same as what we assumed, what we set before we do free body diagram. Okay, if this double arrow pointing outward, we say this is a positive torque. Otherwise, it's negative torque. And the positive torque leads to positive angle of twist. Okay, so the sign of angle of twist is tied to the sign of the torque. Okay, just keep this in mind so that you can calculate positive or negative angles of twist. With these signs, you can do the sum. Otherwise, you will have errors and mistakes. Okay, but these negative, positive signs are just less important, less significant when you do free body diagram, because you have already the directions of the angles. So you can just set positive or negative as you want. Okay, but when you calculate the angles of a twist, right, you'd better calculate them with the signs, with positive or negative signs, and then you can sum them together. Okay, the first example is here, so I will not go through it now. I may leave it to next time or upload a video later. Okay, so that's all for today.
Can you go back to example 2? I didn't get everything copied.
Example 2.
Yes.
Okay. Okay, here.
Professor.
Hey, who asked you the question regarding example 2?
I did. It was me.
Oh, you just want the note?
Yeah, I just want to know.
Oh, okay. Okay.
I didn't get everything down.
Hey, Mirzad.
Yeah. You said homework 3 we could turn it on Thursday, right?
Yes, it's fine.
Yeah, we lost points for it.
No,
I did.
you did get a reduction of points.
Yeah, he said late homework.
A comment.
Yeah.
I will talk to the TA.
Okay.
Other questions?
How will
Hey.
Can you hear me?
Yes, Jackson.
How will the bonus homework factor into our exam scores?
The bonus homework.
Yeah, bonus homework number 2. How will that affect?
Yeah, I will make a decision based on how well most of the students are doing.
Okay.
Okay, so it will be considerable. Okay, will be very, very significant bonus. Okay.